grams. My specific heat is 0.215 calories per gram degree Celsius. And my change in temperature is 28.85 minus 70. Final minus initial, and that would be degrees Celsius. Figure out how much energy was lost. We should get a negative number because it lost it. And I'm getting. So we're around 240. Somewhere went way off.
13,
So you got 310?
Yes.
Anyone else got 310? Then you want to get a different number. What'd you get?
Same.
You got the same?
I'm just not doing the same.
Oh,
Okay, we got that same.
Look at negative 432.36.
I got that too.
442. Wow, that was.
Should we subtract?
Oh, yeah, I know what my stupid error was. 4 times 5 is 20, not 10. All right.
Should we subtract the change 4?
Yes.
Okay.
I mean, it is possible to do it afterwards, but it's just far more complicated that way. Yeah.
All right. They were right.
Do what's in the parentheses here first before you do the rest of it. So 4, what was it again?
Negative
Negative
442.36.
Units?
Degrees Celsius.
I heard somebody say it. Calories. All right, we haven't actually finished checking our answer. That is just how much was lost. That is supposed to be how much the energy the water gained, so let's double check that. So this was for the aluminum, and then for the water, we had 50 grams times 1 times final 48.85 minus the initial. And I think it's somewhere around positive 442.36. 0.5. And hopefully you recognize that as close enough. So, with one loss, the other gained. Questions to hear before I make it seem more complicated, but actually make it easier.
You could just assume that all of the I guess the 0.2 difference, 0.1, is that, would you assume that would go to the environment and the surrounding?
No, that goes to the rounding. Because that 28 point, this number here was rounded, which affected those. If you actually figured out what that full number is and didn't round it all, they should come out much closer. But still, out of 400 plus, we're off by 0.14. You probably feel good that you've done something right. All right, let's make it seem more complicated. T initial for water, and T initial for the aluminum. So again, got the aluminum block, 7 degrees Celsius. Oh, yes, sorry, Vina.
For the part of the middle, like in the middle of the equation,
This,
there, right there in the middle, yeah, yeah.
there,
So
okay.
we would multiply because it's outside
Yes. The official math term is distribution, or distributing. Is that sufficient? Any other questions before we look at this slightly differently? All right. This time, I'm gonna give you the final temperature, and we have to figure out how much water there is. So, let's put this at, like the final temperature, TF, to be 30 degrees Celsius. How much water is there? Well, I know the aluminum block is gonna lose, I can figure out how much the aluminum block's gonna lose with these numbers here. Plug into our magic formula of Q equals MC delta T. So that is 50 grams times 0.215 calories per gram degree Celsius. And what's my change in temperature?
The 30? Is that the change temperature?
It's not 30. Not 10. Not 50.
40?
Thank you, yes. Well, almost. Sorry? Yeah, there we go. Final minus initial. Change is always final minus initial. This is for the aluminum block. My final temperature is 30 degrees Celsius. My initial temperature is 70 degrees Celsius. So negative, of course.
Oh.
And that's 430 calories, negative 430.
Yeah.
Good.
This is not what we're doing right now, but I was gonna ask if the specific heat changes as it goes from like one form to another.
Yes.
We do final minus initial for specific heat
Oh,
to find out.
I haven't run into any equations where we dealt with change in specific heat. I mean, there's a change in it, but where we actually have to calculate the change.
Okay, we would just use the initial specific
Like-
heat of the form.
When we get to talk about phase changes, that's when it happens. So if I have something that's ice and I'm gonna take it up to steam, I have the specific heat of ice and I do that till I get to 0 degrees Celsius, to get to the melting point. And then I have energy change there to melt it. And then specific heat of liquid water up to 100 degrees Celsius. And then I have phase change, and then from 100 to whatever the final temperature is, using specific heat of steam. So you do it in parts.
Okay,
Is that sufficient?
I think so,
All right, so I got negative 430 calories here. How much energy will the water gain? Oh, wait, sorry.
Random question. Does the initial temperature for H2O, is that a part of this, or?
That will be in a moment.
Okay, so,
This was just the aluminum. The aluminum goes from 70 degrees Celsius till
Oh.
they both are at 30 degrees Celsius.
okay, cool, sorry.
Good now? All right. So back to, somebody might have answered it. How much energy is the water going to gain in this experiment?
430.
All right, I think I just heard it over here. It might have been said over there. Maybe I should stand over here more often. How much will it gain?
430 calories.
Okay, 430 calories. So when I try to figure out how much mass of water I have, I'm plugging into the same equation there, Q equals MC delta T, except now I know what Q is. It's 430. Calories. is equal to my mass, which I'm trying to find, my specific heat, luckily 1, and the change in temperature.
No, 40 degrees Celsius?
Not-
Is it switched or is it negative 40 again?
Negative
10 degrees Celsius.
Oh wait, we're talking about water, so
Yeah, just the water.
20 degrees Celsius?
That's not the change.
10.
Okay.
Oh.
We start at 20, we go to 30.
Negative.
That's it, Brianna, you said 10 earlier? Yeah, okay. I can do this first bit in my head. 1 times 10, got that. So I have 430 is equal to 10m. I'm solving for m, so I divide by 10. So my mass is 43, what?
Grams?
Like you mean it.
Grams?
So I have 43 grams of water. What is the volume of the water? How many milliliters?
43.
43.
How many cubic centimeters is it?
43.
Yep. All right, so that's specific heat problems. And I know what you're thinking. You're thinking, my life's just a little bit better right now. We're knowing this. We're seeing this. But it could be better. If only we would do Newton's law of cooling next. Any questions before I talk about Newton's law of cooling?
Is it the same as this, but just negative instead of positive?
No. Newton's law of cooling is specific to the situation of, let's say I've got a hot block in my hand and I put it into a really large space so that the large space doesn't really change temperature significantly. Unlike this, where I put it into the cool water, the temperature of the water will change significantly. Newton's law of cooling. Now, one thing that I did not bring into this problem is time. And bringing time into this type problem is well beyond the scope of this course. However, we do need to consider time when something is cooling off. It's going from 70 degrees Celsius down to 30 degrees, or going down to whatever the temperature of the environment is. Because we're now dealing with a situation where, again, we have some object that's either going to heat up or cool down when it is put into a really large environment. So just imagine small cube, 70 degrees Celsius, I put it into this room, and we look at the temperature change. So let's stick with our 70 degrees Celsius block of aluminum into a 20 degrees Celsius room. So these are the two things I'm working with here. And again, Newton's law of cooling, one of the conditions is that the room temperature is not going to change with any significance. So we can't really use MC delta T because in this scenario, delta T is 0 here, or close enough to 0. All right, so the first thing you need to figure out is what is the most amount of temperature that the aluminum will lose?
Negative 50 degrees Celsius.
Right. So at the most, the change in temperature would be negative 50, or it loses 50. So I'm going to set up a little fraction here. This is the most it can change, most temperature can change. Now, let's say that after 10 minutes, it is now 60 degrees Celsius. This number, I just made up the time and I made up the temperature here. So in 10 minutes, how much did it actually lose? the numerator, I got actual loss in time specified. Or specified time, if I wanted to write normal English. So what Newton's law of cooling says is that this ratio is going to be the same for every 10-minute period. So this works out nicely to 0.2, or we can just leave it as 10/50, no problem with that. So the question is, after another 10 minutes, what will the temperature of the block be? It is not going to lose 10 degrees every 10 minutes. It will lose a fifth of what it possibly could lose every 10 minutes. So at this point right here, what is the most it can possibly lose? Yes. Because now it's at 60 degrees, it can, again, you can always get down to the room temperature. So it can lose 40. And we're trying to figure out how much it actually does lose. This is the math problem. So X is 8. See, 8 over 40 is, yeah, it's 8 degrees Celsius. So what is the temperature of the block at the 20-minute mark? Yeah. 52 degrees. Oh, let's do another 10. So at this point, it's now 52 degrees Celsius. After another 10 minutes, what is the temperature? Well, again, let's go back to, I know that the ratio is always going to be, the actual loss over most you can lose is going to be 1050, 1050 or 1/5 for those who want to reduce it. At this point, how much can it possibly lose? It could possibly lose 32 at this point. So now we can figure out how much it actually loses. .4? So the temperature after another 10 minutes, it loses 6.4 degrees Celsius. And so this ends up being 6, so 45.8 degrees Celsius. So every 10 minutes, it's losing a little bit less than it did the previous 10 minutes. Yes?
Where are y'all getting the numbers from? Like, how do we know how much it could possibly lose? Like, for the.
From the coolest that that cube can get is the temperature of the room. So when we started out, it was at 70 degrees. That's the coolest it can get to, and so the difference between those, that's where the 50 comes from. After the first 10 minutes, it's 60 degrees, and again, 20 is still the coolest it can get, so the difference is 40. So that's why we have a 40 there. Does that answer the question? Okay. And because everyone, and no one has actually refuted this, so I'm assuming it's true, everyone wants a graph. If this is the coolest it can get, so that's 20 degrees Celsius, and this is the initial temperature right here, so in our case, 70 degrees Celsius. If we looked at temperature versus time, the graph basically looks like this. It'll get closer and closer to 20 degrees Celsius, never quite hit it. Eventually it becomes close enough that physicists are fine with it. All right. Do you see where I get the 10/50? All right, so Newton's law of cooling is saying that it's gonna lose 10/50ths of what it could lose every single 10 minutes. Or whatever time I put here. So I'm doing 10-minute increments. Yeah, so once we had the 8 degrees here, so -8 is 52 degrees, and then we got -6.4, get us there. Because we're finding change here, and so we have to actually finish it up. Based on past experiences on a test, about half the people who got figured out what X was stopped there, and the other half remembered to subtract it. Is that a question, Elaine? Or-
I was
oh,
curious,
sorry.
the 32, where did we get that from?
Right, so we started out at 70 degrees. So the temperature of the block, that was 2 degrees Celsius there. And then time. In minutes. So after 10 minutes, it was at 60 degrees. After, I have not forgotten your question yet, after 20, it was at 52. And at 30 minutes, another 10-minute block, it was at 45.8. Okay.
Oh, the change then, okay.
It's getting closer and closer to room temperature as we go. So your question is where we got the 40 from, or
32.
the 32?
It
Okay.
was the more-
Since ultimately at the end, 20 degrees Celsius is the lowest it could get. So the first change in temperature, it could lose 50 degrees Celsius.
Uh-huh,
That's where 50 came from.
uh-huh.
And then 40.
Oh, 52.
Then
okay,
32. If we did another block, it would be 25.8.
Okay. I missed that, thank you.
Other questions?